Hello, welcome back. Today, we're talking about testing claims about two means. So our goal is then to understand how to write the hypotheses and state them when testing claims about two means, and also use the p-value method to test those claims. You can also use the critical value method or use confidence intervals. We're going to focus on the p-value method. Now, if you haven't, excuse me, if you haven't seen my previous videos on the basics of hypothesis testing or testing claims about a single mean, make sure you go back and look at those. And also done a video on testing claims in two proportions. So that'd be good to look at that as well. So what we mean by two means is basically we want to compare two different populations with the means. And we're trying to determine then if there's statistical evidence to say that there's possibly some difference between them. Whether one is greater than the other, less than the other, or maybe just not equal. And that's our goal. And here we're talking about samples that are independent of each other. In a future video, I should talk about how to deal with cases where you're comparing the means of two populations that are not independent of each other, but here we're just considering samples that are independent. So if we think about our population 1, call the mean of that mu1, and the population 2, we call it mean mu2, the null hypothesis is simply that the two means are equal to each other. And then an alternate hypothesis could be one of these three. Could be they're not equal. Could be that one is greater than 2, or one is greater than the other, or one mean is less than the other. And also, it doesn't matter which one you call population 1 or population 2, as long as you do the test and interpret it correctly. Now, requirements for this test will be that here we're assuming we don't know the values of the standard deviations of the populations. And so we're using essentially a t-test. The sample populations we assume for simple random samples. We'll assume that unless otherwise we have a reason not to. Also assume they're independent of each other. In the future, we'll talk about differences between independent and dependent samples. And also I'll assume that either each sample is larger than 30, or they come from populations having normal distributions. And I'll just read this part. Says methods here used are robust against departures from normality. So the procedures tend to work well for smaller samples as long as there are no outliers or extreme departures from normality. What that means then is basically that probably even have smaller samples than 30 will probably work pretty well unless there's some reason to believe that this should come from a distribution that has a really non-normal tendencies. It's not shaped like a bell curve at all. So those are requirements. Also, you notice I'm not mentioning actually showing the t-statistic we'll use because it's very complicated. Well, actually, you're going to use StatCrunch to calculate this, and then StatCrunch will do that calculation for us. So in StatCrunch, this is very much like dealing with one sample, testing a mean about one sample. You go to the same place, so stats and the t-stats. Then say to one sample, go to two samples, and either with summary, if you have the sample means and standard deviations, or if you don't, you can also enter the data, or if you already entered the data, you can do that with the data already in StatCrunch. So let's take a look over the right and take a look at our first example. So it says using a 0.01 significance level and the data below, test the claim that the mean IQ score of people with low blood lead levels is higher than the mean IQ score of people with high blood lead levels. Okay, so we're given our summary in this nice table. Something else we just mentioned is that our significance level, or alpha, is 0.01. And then let's think about our hypotheses. So we want to compare then, these are the samples we want to compare, and we know this is the mean, not proportion, because it actually gives us the mean values. It mentions the word mean or average. So our null hypothesis, remember, is that the population means we assume to be equal. And also I'm going to call this is going to be my population 1 and my population 2. But that's just a choice. You could choose the other way, it's perfectly fine. All right, now with that choice, then our alternate hypothesis, where they call it HA or H1, we're also going to compare the means in some way. Now look back at the claim. The claim said, test the claim the mean IQ score of people with low blood lead levels is higher than the mean IQ score for people with high blood lead levels. So the low blood case will be higher than the high blood case. So the low blood case is population 1. The high blood case is population 2. So this is going to be mu1 greater than mu2. Of course, if you do it the other way and reverse these, once it doesn't matter which one you call 1 or 2, then it would be, if 2 is a low blood level, and you put this U1 less than U2, it would work either way. So then Let's go to StatCrunch. And we'll plug these values in. And also let me write this, kind of jot this down. So one thing to mention right away, if you notice that our sample size for our for our second sample is actually not greater than 30. Now, that's something we probably need to keep in mind. But as we said before, these tests are usually pretty good from samples less than 30, as long as it's not significantly less, and also if there's no reason to believe that they're unusual in some way or very, really far departure from like a bell curve shape. So we're going to assume that. This one's going to go to StatCrunch. Okay, so go to Stats. In any case, go to T-Stats. Since we don't know our population standard deviations, we're going to go to T-Stats. Then we go, in this case, to 2 samples. You have choices of your data with summary. Choose with summary this time. And then what's going to be called number 1, the low blood lead level case. And so this time our sample mean was 92.88. Standard deviation was 15.34. And the sample size was 78. And then the second, population 2, the mean was 86.9. The sample standard deviation was 8.99. And the sample size was 21. Okay, now make sure our hypotheses are correct. So null hypothesis, and remember we can also write it in this form, mu1 minus mu2 is equal to 0. And here we have the choice either greater than, less than, or less than or equal, less than or greater than. And here, since there was mu1 is greater than mu2, here we're just simply writing this alternate form. You see my video on testing claim about 2 proportions. We talked about this, but basically just use the same, as long as you have mu1 minus mu2 and your mu1 and mu2 is the same order, just use greater than. In this case, it was greater than. That will still be true. Will still be greater than. And then hit compute. And then let's copy this table and paste it into our Word document. And also we can come back to this later if we want. Okay, now let's take a look. Let's write down what we need. Now, so look at our main thing we need is our t-stat and our p-value. So our t-stat, or t-statistic, is 2 decimal places, 2.82. And our p-value is 0.0132. Okay. So we imagine what this looks like then. Imagine our standard normal distribution, right here in the middle, is mu1 minus mu2 is equal to 0. And we're talking about greater than, so here's our p-value over here. It's the one-tail test. And if we compare those two, remember we want to compare the p-value to alpha. And recall that our alpha was 0.01. So if we compare those, 0.01 and our p-value, which is 0.0132, you can see the p-value is larger, though not by much, but it's still larger. Okay, as it is larger, then based on this confidence level, this critical, or this confidence level, significance level, then we have to say we cannot reject the null hypothesis in this case. So I'll say, so do not reject. Okay, and I'm going to circle that. So we do not reject the null hypothesis. Oops. Right. Let me try that again so I don't go over something I need. So we do not reject the null hypothesis. All right, so then to summarize this, the claim was that those with low blood lead levels had a higher mean IQ than those with higher levels. And so there's not enough evidence to support the claim. It could still be true, but based on this test, there's not enough evidence. So not enough evidence to support the claim. So we'll say that those with low blood lead levels have higher mean IQs. And also say all IQs, I'll say at the 0.01 significance level. I'll just abbreviate that. Okay, so let's repeat that. So basically from this test, there's not enough evidence to support the claim those with low blood lead levels have higher mean IQs than those that have higher levels at this significance level, 0.01 significance level. Now, you notice we used a 0.05 significance level, we could have rejected, but that's not what we chose. And generally what, what you don't do is then try to go back and try and choose. You want to choose your significance level before time, which usually that's based on some reason you choose a high significance level to begin with. So although you might remark and say, well, it could reject it, you could say that you could reject it if it had been higher, but still, usually there's a good reason for choosing the significance level that you do, so we still have to reject it in this case. So it doesn't mean the claim isn't true. It just simply means that basically, based on this test, with these samples with the significance level, then we cannot reject the null hypothesis, so we can't support the claim. Okay, let's take a look at example number 2. Okay, so this one says, using a 0.05 significance level in the data below, test the claim that Disney animated children's movies and other animated children's movies have the same mean time showing tobacco use. So once again, just for simplicity, let's call this population number 1 and population number 2. This is population number 1, this is population number 2. And our alpha is 0.01, everything's summarized, 0.05 rather. Everything is summarized nicely in this table. Let's write our hypotheses. So our H0, once again, like before, is that the population means are equal. But our alternate hypothesis, either called H1 or HA, once again, it says, test the claim to have the same mean time showing tobacco use. So actually, in this case, it's another case where the claim is actually the same as the null hypothesis, and also doesn't mention anything being greater or less than one or the other. So here we'll say that the alternate hypothesis is that mu1 is not equal to mu2. And we'll see if there's enough evidence to reject the claim. So I'm just going to go back to StatCrunch, and let's take a look at this one. And let me quickly jot these numbers down. Okay, so let's take a look at that. So you can go to the same place, go to stats, and once again, we go to t-stats because we don't know the population standard deviations, which we usually would not. Now, if we did happen to know those, we could actually go to z-stats, but in this case, we don't. So let's again go to toSample, then with summary, since we have the summary values. And let's type in, so number 1 was the Disney values. So our mean was 61.6. Our standard deviation was 118.85. And our sample size was 33. And the second one, for the other movies, the mean was 49.3. Standard deviation was 69.3. And then the sample size was 17. Here again, The second sample is not larger than 30, but once again, we're going to assume for now that the distribution of the second population is close enough to being normal, or at least not that unusual, so we can still use this. Okay. Now, then check our hypothesis test. So remember, this is mu1 is equal to mu2. So mu1 minus mu2 is equal to 0 is the same as saying mu1 equals mu2. And here we just use the same symbol we use there. So mu1 minus mu2 is not equal to 0. And then hit compute. Same thing. Once again, let's copy this and we'll plug it into our Word document. And also we'll close it. And once again, notice here we can come back to that one and the previous example later if you want. And let's paste that here. And let's write down. So what we need is our t-statistic and our p-value. And so here's the t-statistic is 0.3, approximately 0.33, which is not very large. So it's unlikely we'll reject the mean, but we'll see. So 0.33 to 2 decimal places right here, 0.333 and so forth. And a p-value is last on the right, and it's, yeah, so 0.7406, which is very large. Just imagine we're not going to be rejecting. So if we think about this, our standard normal distribution with our mu1 minus mu2 is equal to 0. In this case, it's a two-tailed test because they're saying it's not equal to something. So remember how this would work would be, we'd have our half of our p-value over here. So p-value divided by 2 here, p-value divided by 2 here. And then if the p-value once again is less than the critical value, less than the significance level, we reject. As we'll see, we're not going to be able to in this case. So we compare the p-value and alpha. Our alpha is 0.05. And our p-value was really large, so 7406. And clearly we cannot reject. In fact, it's hard to imagine a level where we could reject that thing would have used. So p-value is clearly larger, so we don't reject the null hypothesis. Okay, let's go back and look at our claim, and then I want to summarize this in a meaningful way. Once again, the claim was that's the claim that Disney animated children's movies and other animated children's movies have the same mean time showing tobacco use. So there's not enough evidence to reject that claim. So we'll just say not enough evidence to reject the claim, or to support the claim, rather. Well, yes, let's see. So you could say this different ways, but let's try to be kind of state as much as we can the way it's stated. So the claim that Disney animated children's movies and other animated children's movies have the same mean time showing tobacco use. There's not enough evidence to reject that claim. There's not enough evidence to reject the claim that Disney and other animated children's movies have the same mean time showing tobacco use. And once again, that's tobacco use. And then we'll say at the significance level we have at 0.05 significance level. Abbreviate that level, of course, with such a high p-value, you probably can reject it pretty much any useful significance level. So what that means is that basically we can't say for certain that there's, based on this, we can't support the claim there's any difference between them. There could be, we can't say. Now also you might wonder why, since there's a fairly big difference in the means, why we couldn't reject that. And part of it is because, look, the standard deviations are actually really large, okay, especially compared to the means of cells. So basically, in fact, in both cases, they're larger than the means. So that's one of the reasons we couldn't, because there's so much variation in the data itself that we weren't able to reject. So it's possible had the standard deviations been a lot smaller, we might have been able to reject the null hypothesis, but that's not the case. In this case, so we can't say, we can't reject the claim. It doesn't mean that the claim is true, just that we can't reject it. And then the last one, let's take a look at our last example. Okay, and this one says, weights of quarters are carefully considered in the design of vending machines. Results of samples of pre-1964 quarters and post-1964 quarters are given below. Once again, I'm going to call this my population 1 and my population 2, so we just have to be careful how we say this. In fact, maybe we change it. May want to actually decide that afterwards. The use of 0.05 significance level tests the claim that the post-1964 quarters have a mean weight that is less than the pre-1964 quarters. So actually, in this case, I think it will actually call this population number 1 and population number 2, just to kind of use the less than, say it is less than, although it doesn't really matter as long as you have the sign pointing in the right direction. Okay, so our alpha is 0.05. And let me go ahead and jot everything down. Okay. Now, let's do our hypotheses. H0 is that they're equal. Okay, so mu1, the population means, are equal. And then it's always the case with these, the way we do this here. And then our alternate, H1 or HA. So let's read the claim again. Test the claim that the post-1964 quarters have a mean weight that is less than the pre-1964 quarters. Okay, so this is post is 1. This is our second population. So here we're going to say that mu1 is less than mu2. That then is our alternate hypothesis. Okay, so let's go to StatCrunch. Like this, since I've jotted everything down, I have to come back and look at it. Okay, so once again, same place, go to Stat. Once again, T-Stat, since we don't know anything about the samples or know anything about their standard deviations, you go to ToSample, once again, with summary. And then, okay, so for population 1, that was the second one. So let me type that in. So well, I apologize. May I actually have to go back for a second if I can make sure and read my writing correctly. There we go. Okay, so the mean of sample 1 was 5.63930. The sample standard deviation was 0.06194. And the sample size was 40. And then for the second, which we call number 2, is the pre-values. The mean was 6.19267. Sample standard deviation was 0.08700. And the sample size is also 40. So in this case, both samples are larger than 30. So even if they're not from normal distributions, we're confident that we can use these methods. And then our hypotheses, once again, the null hypothesis, mu1 minus mu2 equals 0 is the same as mu1 equals mu2. In this case, once again, we want to go with, it was less than, let's double check that, right? mu1 less than mu2. And so I want to make sure we have that. So we use the same sign here. Okay. Because mu1 minus mu2 is less than 0 is the same as mu1 minus, or mu1 is less than mu2. Okay. Check, make sure everything's correct. Then hit compute. And the same thing again, we'll take this and put it into our Word document. So we'll close this. Okay, and then let's collect our data that we need. What we just need are the t-stat, and the other value. So the t-stat, the t-statistic, is equal to, well, it's really a negative. So negative 32.77. So obviously we're going to be rejecting here. And then the p-value is equal to, or actually not equal to, it just tells us that it's really small. It just tells that it's less than 0.00030 than 1. Less than 1 in 10,000. Okay, so same thing. Let's compare. Well, first I'll just draw a picture of what this would look like. So here's our standard normal distribution. It should be symmetric. And here's mu1 minus mu2 is equal to 0. So we're talking about less than, we're talking about way over here. And this is our p-value, the area under that curve. And so if that's less than our critical value, then we can reject. So once again, the same comparison as before. So in these p-value methods, we do comparison the same way each time. So compare the p-value, alpha, and our alpha was 0.05. And our p-value was less than 0.0001. So clearly that's less. That's clearly we can reject the null hypothesis. Okay, this time we can reject the null hypothesis. So let's look at our claim, see what that means then again. Make sure we state it in a meaningful way. So the claim was that post-1964 quarters have a mean weight that's less than pre-1964 quarters. There's enough statistical evidence to support that claim. Enough evidence to support the claim. You write that a little bit better. Claim that the post-1964 quarters have a smaller mean weight than pre-1964 quarters. At the 0.05 significance level. Okay, so once again, what that means is, since we can reject the null hypothesis, that means we have enough evidence to support that claim that these post-1964 quarters do have a smaller mean weight. Do a better in there. Smaller mean weight than the pre-1964 quarters at this 0.05 significance level. And actually, that would also be probably valid. We could reject the null hypothesis, probably pretty much any significance level we would use. Okay, so once again, let's review what we learned. So we learned how to test a claim about two means. And once again, with the method, we just learned how to set up the hypotheses. Basically, we have, similar to the test about one mean, we have three possibilities for alternate hypothesis. We have that the means are equal, or that one mean is larger than the other, or one mean is smaller than the other. And then the null hypothesis is always that they're equal. And then we learned the basic using the p-value method, and it works exactly the same as it has in previous methods, previous tests, and we're able to either reject or not reject the null hypothesis based on that. Thank you. Have a good day.